Hello everyone. I'm very grateful for the organizers of this TPRA workshop for conducting the shared task, which allows me to present my work. My paper is titled Our paper is titled Domain Identification of Scientific Articles using Transfer Learning and Ensembles. I am Adeep Hande, who is going to be presenting our work. Our research focuses on the development of transfer learning approaches and leverages ensembling to achieve the best performance. This paper is a joint work of Indian Institute of Information Technology, Tiruchirappalli, Ultra Arts and Science College, Tamil Nadu, and Insight SF5 Research Center for Data Analytics, National Institute of Galway. Here we are going to give an outline of the paper. The paper is, our presentation is mainly divided into four major things. One is we define a problem statement of the shared trust. Then we'll be going to discuss about our dataset. Then we will talk about the methods that we have used to evaluate the shared task. And lastly, we compare the results of our methods. Now, moving on to the domain identification. The shared task was provided us with the abstracts of a paper. The organizers had collected nearly 35,000 scientific articles and had belonging to the computer science domain, out of which there were 7 classes. An abstract, it's a brief summary of a research article summarizing the whole paper and the intention of the author. This is how an abstract looks like. So as the size of an abstract is usually less than 250 words, we will be considering this as a sequence classification task. If the size of the article were more than 250, we would have to go for summarizing and then try for sequence classification. However, as the maximum length of the articles are less than 256, we would be going for treating this as a sequence classification task. The table 1 displays the class-wise dataset distribution for train, test, and validation. We can see that there are 16,800 abstracts in the train set, 11,200 for the validation, and 7,000 for the test set. We can see that there are 2 classes, namely distributed and cluster computing, and software engineering, whose the support in the test set is less than 800, including logic and computer science, which consists of only 772 articles, whereas the test set and the validation set consists of 1,811 and 1,270. So there are total 7 classes. All of these belong to computer science domain, as the organizers had initially classified the abstracts belonging to the domain of computer science. So our approach in treating the sequence classification will mainly be in the direction of transfer learning. We know that transfer learning leverages on the previous information learned and will tend to perform better than learning from scratch because of it. Then we try to come up with approaches that can achieve better performance than our transfer learning approach. So we know that transformer block is a pinnacle of the NLP in recent years, mainly owing to its success over recurrence networks (RNNs). We know that almost all models have taken a transformer block as its building block of architecture. It is worth noting that BERT, Roberta, and Cybert, all of the models have the base model as BERT itself. That is, all of Roberta and Cybert are based on BERT base. BERT-based is a pre-trained language model that is trained on monolingual unlabeled English text. It is trained on 16 GB of data. While Roberta is similar to BERT, however, it differs in the amount of training data and its retraining strategy. Roberta is pre-trained on 160 GB of data, and they have disregarded the next sentence prediction loss, which did not prove useful during pre-training. However, Cybert is a domain-specific BERT-based language model. The main reason is that Cybert is essentially a BERT model that is pre-trained on scientific articles. But it's worth noting that scientific articles here, the pre-trained during pre-training, the scientific articles used are 85 belong to the biology domain. 85% of the scientific articles belong in the biology domain, while the rest 15% belong in the computer science. So the main reasons towards this approach is mainly due to the availability of our scientific papers out there with more number of papers in the direction of biology because it is more required, as in there are more number of researchers devoting time to that. Now figure 1 shows how we are fine-tuning the retrained language models and then try to compute their probabilities for ensembling. We can see that an input sentence in an abstract is essentially preprocessed first by removing the formulae, and then they are passed on to as tokens by tokenizing based on the model. BERT has its own BERT-based tokenizer. The tokenizer is structured as follows, with an initial CLS token followed by the tokens of that input sentence. We can see that the output token C consists of the class label, which is then the output label C has the class label which is all nothing but the probabilities too. We use a softmax function to obtain the class-wise probabilities of the function. This is how a BERT-based model is fine-tuned. Initially, a BERT-based parent BERT model, it can be BERT-based uncased, or Roberta-based, or Cybert uncased, and we will be having a linear layer over the top of the parent model so as to classify the labels. As there are 7 classes in our dataset, we will be having the output shape as 728,7, where 728 is the number of hidden features in all of the BERT-based models. Essentially, this will be going on towards the ensembles here now. After discussing the 3 models, we after computing the probabilities of the 3 models, we aim to create a soft coding strategy, or maybe we had an approach to average the probabilities of all of the classes and then have a model to see if that approach improves any performance. This is a purely experimental based approach. As stated earlier, this is the formula of computing the softmax function, where I represents where Z represents the number of classes, K represents a number of classes. Or another approach was to, instead of taking the average where all of the classes are given equal weights, we thought of having a weighted average for the probabilities. In order to calculate the weight, we had an initial approach of using Pearson correlation to compute the weights for predicted probabilities. Pearson correlation is computed by finding the correlation between the output label and the initial output probability and the initial probabilities of the data set. we will be discussing the results in the further sections as we have talked about in methodologies. Now, this is a system architecture describing how we computed the predictions. A given abstract is the has preprocessing done towards it. As stated earlier, the preprocessing involves removing the formulae and other numbers. One of the main reasons to remove the formulae is because they usually tend to have a Greek letters as eta, theta, pi, epsilon, etc. However, all of the Bird, Roberta, and Cybert are trained on unlabeled and monolingual English text and will output an unknown token as they will have not been pre-trained on this Greek letters usually present in the formula. This is the reason why we are removing all of the Greek letters and formulas from the abstract during preprocessing. Then thereon, we'll be using Roberta, Bert, and Cybert by fine-tuning them for sequence classification. We use Huggy transformers and PyTorch for computing the probabilities, as Hugging Face transformers have the Bird for sequence classification function, which is easier to compute and code. Then we will be using ensembling as in E1 and E2, which are then thereon to compute the predictions. This represents the results on validation and test set. We can observe that Bird is the least performing out of the 5 and E2 as in the weighted average has the highest probability, highest weighted F1 score among the 5 in validation set. We can see that the averaging probabilities E1 did not perform better than Cybert, and this was the reason why we didn't choose E2, as in this the results of E1 motivated us to go towards the weighted average. Hence, for our test submission, we have submitted Cybert, E1, and E2 to the organization. And from the results, we can see that Cybert has an F1 score of 0.9227, while E1 has the lesser score of weighted F1 score than Cybert, and E2 has a weighted F1 score of 0.9246, having the best results among all of the 5 models. We can see that E2, the loss function we use is a cross entropy, which is a standard loss function used for multi-class classification algorithms in both computer vision and natural language processing. Table 4 represents the classification report of E2 on the test set. From here, we can observe that cryptography and distributed DS has the most score of 0.98, which is data section algorithms, while CR, which is cryptography and computed systems, has the least score of 0.8. We believe that the less support is among the many reasons why CR is performing very poorly in comparison to the other 6 classes. Hence, we conclude that our approach of E2 to compute the weighted average of the predicted probabilities of Cybert, Roberta, and Bert achieves the best performance in all of the 5 models. This confirming that the approach of ensembling, which leverages the various representation learned from multiple weaker models to have a robust model that performs better than the rest of the models. Thank you. If you have any doubt, please feel free to mail me. Thank you.